Hello, and welcome to your third linear regression lecture. Now, even though this is technically a linear regression lecture, the ideas we're going to talk about apply to literally all of the different machine learning algorithms that we are going to learn in this course. First, I want to talk to you a little bit about the ideas of bias and variance. In data science, we basically have two types of data. We have data that we have now and future data that we want to make predictions for. The problem with this is that when we fit our model, we only have the data that we have now. By definition, we're not time travelers, so we can't go into the future and get future data. So all we have when we're fitting our models is the data we have now. Now, when we're fitting a model, one extreme that we want to avoid is having a model that is too simple to capture the relationship between our inputs and our output. For instance, here we have a relationship that honestly looks pretty curved and nonlinear. If we fit a linear model to this data, that's far too simple of a model to accurately capture the relationship between our input and our output. On the other extreme, we have a model that is really maybe far too complicated. In fact, it basically perfectly predicts every single data point that we've seen. For instance, maybe this is a polynomial regression with a lot of degrees. Now, if we look at these models, it might seem like the overcomplicated model is much better than our too simple model because it's perfectly predicting every single data point, whereas our simple model has a lot of errors, like you can see here. But we're only looking at the data that we have now. And typically when we're building machine learning models, we want our model to make predictions about data that's going to come to us in the future. So what happens when we have that future data? Now, when we look at this future data, we see something interesting. When we look at the model on one extreme that's far too simple, it's still doing pretty badly. This model just does not have enough flexibility to model the true relationship between inputs and outputs. So even on future data, just like the data we've seen before, the model does pretty badly, but it's consistently bad. On the other hand, with our extreme of a model that is far too complicated, now we see that there is a large amount of error when we use this model on data we've never seen before. And this is a huge departure from how the model did on data it had seen. It was perfectly predicting every single data point, and now we actually see a large amount of error. This is at the heart of the bias-variance trade-off. When we look at this graph, we can see that the x-axis represents the model complexity, with items on this side of the axis being low complexity and models here being really high complexity. On the y-axis, we have a measure of error, so how well our model is performing. The two different lines are looking at data the model has seen before, so data we use to train the model, and then data that it has never seen before. This is like our future data. This graph represents the bias-variance trade-off, and as we talked about before, we want to avoid the two extremes. On this extreme, we have really high bias. This is where our model is far too simple to explain the relationship between inputs and outputs. So no matter what data you give it, whether it's seen it before or not, the model does extremely badly. It has very high error. This is called underfitting. When our model is too simple to explain the relationships between our variables, we have a model that is underfit. Underfitting is characterized by having really poor performance in both data our model has seen and has not seen. Again, underfitting is when we have high bias. In the other extreme, we have overfitting. Overfitting is when our model is far too complicated, so it overfits to data it's seen before and doesn't generalize well to data it's never seen. We can see this pattern by looking at the fact that the error is incredibly low for these models on data it has seen before, but incredibly high on data that it has never seen before. This pattern where there's a huge difference between the performance of the model on data it has seen versus hasn't seen is called overfitting, and it occurs when we have high variance. So obviously we want to avoid both of these extremes, and hopefully we'll end up in this Goldilocks zone where we don't have high bias nor do we have high variance. We're not overfitting or underfitting. We're just right. This is another graphic that really shows overfitting versus underfitting well. Remember, when we underfit, our model is too simple to explain the relationships between our inputs versus our outputs. In overfitting, our model is far too complicated and won't generalize well to data it has never seen before. It does well on data it's seen, but poorly on data it's never seen. What we want is to be right in the middle. We don't want to overfit or underfit. We want a model that is just complicated enough to explain the relationship between our inputs and our outputs without overfitting or underfitting. So now that we have an intuition for what bias and variance are, let's talk a little bit about what they are mathematically. To review, our goal when we're doing machine learning is to figure out or approximate the function that takes our inputs and converts them to our output. In this equation, that function is represented by f of x. It takes in our inputs and gives us our output. But there's a bit of a problem. If we knew what that function was that takes our inputs and converts them to our outputs, we wouldn't need machine learning. So what we're doing when we fit a machine learning model is we're trying to approximate that function. That little hat that you see on the screen basically tells us that this is a guess or an approximation. So from these equations, you can see that there are two sources of error in our model. The first type is irreducible error, which is represented in our equation here. This basically says that even if we had the literal correct perfect model, we would always have some error in our guesses. This could be due to features that we didn't include in the model or just natural random variation. And irreducible error is irreducible. We can't really do anything about it. We're just stuck with whatever it is. What we do have an effect on is the reducible error. Reducible error occurs because our approximation of the function that takes our inputs and converts them to our outputs is not perfectly estimating what that true relationship is. And this is what we have control over. We have no control over the variation in the data, that irreducible error, but we can try and make sure that our model is as close to possible as the real model. Here enters the bias variance trade-off. And this is the thing that consumes all data scientists almost all of the time. Here on the screen, we have a pretty complicated formula, but we're going to break it down. This formula encapsulates the bias variance trade-off. This equation says that the expected mean squared error at a certain point is equal to this entire equation. The expected mean squared error for a point basically means if we fit different models with different samples of data over and over and over again, and then compared the prediction to the actual value x0, what do we expect that error to be? Well, when we look at the right-hand side of the equation, we see something that looks very familiar. Our irreducible error. This is something that we have no control over. This is just the natural variation in our data or variables we're not accounting for. We cannot change this at all. What we can change is the bias and the variance of our models. So let's break that down into the two pieces, the variance and the bias. Variance refers to the idea that if we fit our model on different samples of the data, how different would those models be? For instance, on this right-hand side, you can see an example of low variance models. These are polynomial regressions with degree 2. Even though we have different samples of data in each of these quadrants, the models that we're fitting look incredibly similar. These are low variance. On the other hand, a high variance model is going to be a model that is very different depending on the sample that we fit it on. For instance, here in these 4 quadrants, we see a polynomial regression with degree 20. And as you can see, when we have different samples of data, the model looks quite different. This is a high variance model. The other part of this equation is the bias. Bias basically refers to whether we're able to approximate the true model on average. On the right-hand side here, you can see models that have low bias. These models are complicated enough to explain the relationship between our inputs and our outputs. Therefore, they have low bias. On average, we are able to capture that true relationship between input and output. On the other hand, we have high bias models. These are models that are far too simple to explain the relationship between our input and our output. No matter how many of these models that we fit, we are not going to be able to approximate that true relationship. The model is just not sufficient. So as you can see, due to the equation, this creates a bias-variance trade-off. When one increases, the other will tend to decrease. This is what creates that U-shaped curve we saw for unseen data when we looked at the bias-variance trade-off graph. As the bias goes down, the variance tends to go up. So when we look at those two things combined and look at our error, we get this U-shaped curve. Again, our goal is to try and end up in that Goldilocks zone. We don't want places where there's too high variance. We also don't want places where there's too high bias. We want to be right in that middle in the sweet spot. So we've just spent a lot of time talking about bias and variance, and we talked about the related concepts of over versus underfitting. Overfitting, where our model does really well on data it's seen and poorly on data it's never seen, and underfitting, where it does really poorly on both. However, like we've mentioned before, we are not time travelers. We, when we're building our models, don't have access to future data. So what do? Well, it turns out we do model validation. So because we're not time travelers and typically we don't want to wait for future data just to assess our models, what we do is we use model validation to take the data we have now and split it into two sets. Those sets are going to be called our training set and our testing set. Our training set is data that we're going to use as normal to just build our model. The testing set is basically pretend future data. This is data that we're going to set aside and use to assess the model later on, basically pretending that it's future data because we can't actually get future data. Because we're not using our test set to fit our model, it is truly unseen data, which allows us to get some kind of clue for how our model might perform on data it's never seen before. When doing model validation, the first thing we need to do is actually split our data into these two sets, the training set and the testing set. Then we need to train our model. Now we're only going to train our model on the training data. The testing data is supposed to be unseen data, so it can't help us fit the model. Lastly, once the model is completely done, we are going to test it. We're going to see how does it perform based on training data and on testing data it's never seen before. So we're going to talk about three types of model validation. The first one, the train test split, is the most simple. Literally all you do is you take all of the data you have available to you and you split it. Some rows are going to be used to train our model and some rows are not. Those rows are going to be used to assess how our model performs on unseen data. Typically, we want to make sure we have enough data to actually fit our model. So you'll usually see proportional splits like 70-30 or 80-20 or 90-10, where most of the data is being used to train the model and then a small portion of it is being used to see how the model will perform on unseen data. And that's literally it. This is by far the simplest method of model validation, but it's not the only one. Another really common method is k-fold cross-validation. The cross-validation basically refers to the fact that we are not going to fit one model when we're testing it. We are going to fit multiple models. The k in k-fold is just a variable like 5 or 10. And when we do k-fold cross-validation, we basically take all of the rows of our data and we split it into k equally sized folds. So if we had 10-fold cross-validation, we take our data and split it into 10 equally sized groups. Then what we do is we fit a model on k-1 of these folds, leaving one of the folds to be our test set. But we're not done there. We are now going to fit a second model. Each of the columns in this graphic represent a new model that we're going to fit, where the yellow rectangle represents the fold that we're going to use as the test set, and the rest of them are going to be used as our training set to train our model. Basically, we repeat this process where we fit a model using k-1 of the folds, and the last fold is the testing set. When we repeat that over and over and over until every single fold has had the opportunity to be the test set once. Now, as you can clearly tell, this is a little bit more computationally expensive than the train test split because instead of fitting a single model, we're fitting multiple models. But it gives us a better estimate of how well our model will do on unseen data than just doing a train test split. If we take the idea of k-fold cross-validation to the nth degree, we get leave one out cross-validation. Like the name implies, leave one out cross-validation basically is k-fold, where every single data point is its own fold, meaning that we fit the model on all the data points except one, and then look at how well that model predicts the last data point. We repeat this process over and over so that every single data point gets to be the test set. Now, like k-fold, but even more so, leave one out is incredibly computationally expensive. If we have 10 million data points and we did leave one out cross-validation, we would be fitting 10 million models. However, like k-fold, it does give us a better estimate of how our model is going to perform on data it's never seen before. Even with the simple models that we're going to use, leave one out cross-validation can get pretty expensive pretty fast. Typically, we're going to be using k-fold or train test split. And on that note, you might be thinking, we just learned 3 different methods of model validation. How do I choose one? Well, 2 things you want to keep in mind are 1, the size of your data set, both the number of rows and the number of columns that you have. If you have a ton of data, like millions or hundreds of thousands, leave one out cross-validation probably not going to be great for you because you're going to have to fit a ton of different models. Another thing that you want to think about is the computational expense of your model. Now, in this class, the models that we're fitting are incredibly simple and barely take any time to run. So this is not that huge of a consideration. But if you're fitting models that are really complicated, like in the next series in the class, we exclusively do deep learning, those models take a really long time to fit. And even if we were doing something like k-fold cross-validation, fitting 5 or 10 or 20 of these models is prohibitively computationally expensive. So just to review, model validation allows us to assess the performance of our model both on data it has seen and data it has never seen before. This allows us to see if our model is overfitting, underfitting, or if it's doing pretty well. Remember, overfitting happens when our models are high variance. These models tend to do quite well on data they've seen before, but quite poorly on data they've never seen. On the other hand, underfitting happens with high bias models. This will occur when we see training and testing error that are both pretty poor. If our model's too simple to explain the relationship between our variables, it doesn't matter if it's data we've seen or not. They're both going to do pretty badly. And when we looked at the equations, we saw that bias and variance occur in a trade-off, which means if we increase the bias of our models, we actually tend to decrease the variance of them. This allows us to get into this Goldilocks zone that we really want to be in. Let's say we have a model in this zone right here, so it's overfitting. One of the ways we can combat that is we can actually reduce the complexity of our model. That'll hopefully move us from this area of high variance into this Goldilocks zone. Over the course of this class, we're going to learn lots of different ways to do that. But the first one I want to talk about is regularization. In order to talk about regularization, we need to review loss functions. Remember we talked about that loss functions are numbers or metrics that assess the performance of our model, where smaller values mean a better performing model. For instance, in linear regression, one of the loss functions we talked about was the sum of squared errors. Like the name implies, the sum of squared errors takes the difference between our model's predictions and the actual values, squares them, and adds them all up together. One of the ways we pick the parameters of our linear regression models is by minimizing this sum of squared errors. However, we can add something to this loss function that basically encodes this value we have for reducing the complexity of the model so that we can move from overfitting to hopefully a perfectly fitting model. The way we do that in general is just by adding a term to our loss function. Usually it's in the form of something like this. This basically says that we're going to add a penalty to the complexity of our model. This lambda term basically just says how much of a penalty we should add. bad. If that lambda is 0, there's no penalty. If it's really big, we have a really big penalty. So we're going to talk about two forms of regularization that take this form, ridge and lasso. They're super similar, but there are some differences that we'll cover in the end. First, let's talk about ridge. Ridge regression is a method of regularization that can help reduce the complexity of our models. It does so by adding a penalty, just like we talked about. With ridge regression, we penalize the sum of the squared coefficients. Because we're trying to minimize the overall loss function, this penalty means that we are punished when our coefficients are very large. Essentially, this creates a dynamic where our penalty and the typical part of our loss function are sort of battling it out. In order to have a model that fits well, we probably need coefficients that are non-zero. But because we're penalized for having large coefficient values that are far away from 0, we need to make sure that increasing those coefficients does actually improve this side of the loss function. So if making a coefficient far away from 0 doesn't improve the fit of our model, it's basically not worth the penalty we incur by having it be far away from 0. However, if there's a variable that really increases the predictions of our models, then it might be worth the penalty of having a non-zero coefficient. Again, this lambda parameter controls how harshly we're penalizing big coefficients. When lambda is 0, this just reduces to our original loss function, and there's no penalty on the coefficients. If lambda is huge, then we penalize large coefficients a ton. In fact, if we increase this to a really huge number, we essentially would have all of our coefficients be 0 because it's just not worth that huge penalty. Lasso is another type of regularization that looks really similar to ridge. The main difference is that instead of squaring the coefficients in the penalty, we take the absolute value. Again, we have two parts of the loss function that are battling it out. If coefficients are going to be different than 0, we need to make sure that it makes up for it by improving the fit of the model. Now, you might be saying, well, why would you have two different things? They're basically penalizing the same thing. Well, lasso has this really nice property where it actually drags those coefficients to exactly 0. With ridge, it does make the coefficients closer to 0 if they don't improve the fit of the model, but it tends to make them close to 0 and not exactly 0, whereas lasso tends to make them exactly 0 if they don't pull their weight. When we make the coefficient of a predictor 0, it's the same as removing that predictor from the model. So in that sense, lasso does something called variable selection, which basically tells us which of our predictors we should keep in the model. This is a really nice feature of lasso, so if you ever need to do variable selection, lasso would be a better choice than ridge. And again, in general, our whole goal with machine learning is to make sure we're in this Goldilocks zone. So if we have a model that we think might be too complicated, regularization can basically take the model from this region of really high variance and make it a little bit simpler through that penalty, which hopefully will bring us into this Goldilocks zone where we have a model that is neither overfit nor underfit. All right, last thing we're going to talk about is something called double descent. So unfortunately, it turns out that everything I've taught you is completely wrong. When we have really complicated models, for instance, splines or deep learning where this occurs a lot, we actually see a phenomenon called double descent. So from this side over, this graph looks exactly like the graph we've been looking at for the bias variance trade-off this entire lecture. We can see that familiar U-shaped curve where at a certain point, the out of sample or testing error starts to increase as our model overfits. But then we hit this thing called the interpolation threshold. This is basically the point at which our model can literally pass through every single point. It can perfectly predict them. And again, this happens a lot with really complicated models like deep learning models or splines. Now, past this threshold, what happens is we actually see our testing error start to decline again. So this completely ruins the bias variance trade-off that I just told you about. Or does it? What's happening in double descent can be really well explained by splines, although like I said, it also happens a lot in deep learning. In the top two images in this graph, we can see what we're used to. In the left-hand graph, you can see a model that has a moderate amount of flexibility, and you can see that it fits pretty well to the true relationship, which is shown in that black line. This is an example of a model that is neither underfit nor overfit. So we're probably about here in the bias-variance trade-off. On the right-hand side, you see a much more complicated model. This is a regression spline with 20 degrees of freedom, and you can see it is incredibly wiggly. We have now reached the interpolation point. As you can see, this model perfectly hits every single data point in our data set. And you can see that that creates quite a wild and wiggly model. In fact, we're probably way over here, where this model, we don't expect it to generalize well to data it has never seen before. But what's going to happen is we are going to keep increasing the complexity of this model. For instance, in the bottom left-hand graph, we see a model with 42 degrees of freedom, so a much more complicated model. However, when we look at the model that's actually fit, it looks a lot smoother and less wiggly than the 20 degrees of freedom model. What's happening here is once we pass the interpolation threshold, there are actually multiple forms of the model that could perfectly interpolate all of these points. When we were at this 20 degrees of freedom point, there was only one possible model, given the flexibility we had, that could perfectly hit every single point, and it was a bit weird. However, with even more degrees of freedom, that means more flexibility, which means there's actually multiple forms that can hit every single point. So how do we choose between them if they're all perfectly predicting our data? Well, it turns out that we choose the model that is the smoothest or the least wiggly. And because of that, this model, even though it has technically more flexibility than this model, it'll be smoother and therefore generalize better to unseen data compared to this model. That's when we start to see this second descent. As we increase the flexibility of our model past the interpolation point, we actually see the out of sample or test set error start to decrease again, because even though our models technically have more flexibility, the way we choose the model out of all the models that could interpolate the points forces us to choose the smoothest option of all of those models, thus leading to that second descent. So I guess I sort of lied. This does not break the bias variance trade-off at all. All it's saying is we need to be careful about how we're measuring model complexity, because sometimes with certain types of models, as we increase complexity past the interpolation point, we actually tend to choose smoother models than we do at the interpolation point, thus leading to this double descent. All right, that's all I have for you. I will see you next time.